All right, so this lecture is going to talk about vaccines. Basically, they're a mechanism for how we try to prevent infections. So I wanted to start with just a overview of how many vaccines and the types of vaccines that the CDC suggests or actually kind of requires for children in the United States to receive. So this is the birth to 18 years. If your child goes to a public school, then they have to have proof of immunization, or you have to have documentation that you have a religious issue against immunization. What's interesting is we're finding as people are opting out of immunizations, we're seeing some diseases, pathogens that we haven't seen show up much, show up again. So we'll talk about that in a little bit too. This is a schedule for adults with certain medical conditions. So if you're immune compromised, for instance, they may not recommend you getting all of the vaccinations, or they may recommend you getting additional ones. And this one pertains to you all for your 19 plus years old people. They recommend your flu shot annually, your tetanus shot once every 10 years. There's the chickenpox, and then zoster. So varicella is the chickenpox, zoster is the shingles vaccine, and we'll talk about that vaccine. Human papillomavirus, we'll talk about that one. So lots of information on the CDC website, and of course your doctors would know which vaccines you should be getting. This I think is kind of interesting. Here's the difference 30 years can make. So between 1983 and 2016, recommended 70 vaccine doses, 51 injections. As a person who hates shots, that number scares me. Of course, you can see that this is including a yearly flu shot. And this meningococcal one is a newer one that's come out, and I think they're actually even recommending college students get this to prevent a serious meningococcal infection. And so we'll talk about that one too. So a little history. You probably heard of Edward Jenner and the cowpox vaccine. So the idea was that milkmaids, women who were milking cows, would get these pustules, these open sores on their hands, and they realized that in addition, these milkmaids never came down with smallpox. So smallpox was going around at the time. Smallpox is a fairly deadly disease. We'll talk about that in a minute. And so Jenner hypothesized that the cowpox was somehow providing immunity or protection to these milkmaids against smallpox. So the trial he did was he took this little 8-year-old boy, not his son, somebody donated, that sounds funny, donated their child to this vaccine trial, and he inoculated the boy with cowpox. So he scraped off some of the pustule from a milkmaid, scratched the surface of the child's skin. The child developed a pox or a pustule as well, and then later challenged with smallpox, which means he actually infected this child with live smallpox virus. Amazing how science was done back then, right? And the boy did not develop disease. So this gave support to Jenner's hypothesis that cowpox could somehow protect people against smallpox. And so this was the first vaccine. And the name vaccine, or the term vaccine, comes from vaca. And vaca means cow. The smallpox vaccine we then used later was again a related. We were not injecting people with smallpox virus, which is called variola, but instead with a vaccinia virus, a related one. So another important point here is that a related virus could provide protection. And we'll talk a little bit about how related something needs to be in order for a vaccine to work. So the goal of a vaccine is to prime the immune system. So we've talked about the innate and the adaptive immune system. And so a vaccine is basically going through the innate and priming the adaptive, right, to generate those memory T and B cells. Okay, so your goal of a vaccine is to get adaptive immune response. When we talk about some papers that are looking at developing vaccines, we will talk about how they have to actually measure. Did they get all the way to, excuse me, stimulating that adaptive immune response? So let's head back to smallpox. So this is an image of a man with smallpox. You can see he is just covered with these bumps, right? And smallpox has a 20 to 60% mortality rate. Okay. And a lot of it depends on the health of the person who has been infected, high enough that we wanted to try to get rid of this disease. So smallpox was eradicated, which means we consider it wiped off the earth in 1980. And the program to eradicate it went from 1966 to 1980. So really in a fairly short time, 14 years, they were able to do global immunization. Okay, so this wasn't just done in the US or the Americas. This was done worldwide. And through this global immunization, we were able to get rid of this virus. Okay, so smallpox is caused by the virus called variola. Okay. It's a enveloped DNA virus. And the reason we were able to eradicate this is there's no reservoir. Okay? It is only spread by human to human contact. Okay, so smallpox cannot hang out, Smallpox cannot hang out in the environment, it cannot hang out in animals, it doesn't infect anyone else. And so by eliminating the host, we didn't eliminate humans, by vaccinating the host so that it would mount a defense to smallpox, the virus had no place to replicate, no place to hide out. And you're going to see that that's not true for the virus polio, which we're really close to eradicating, but haven't quite made it. Interesting little fact, they found evidence of smallpox on a mummy all the way from 10,000 BC. So this virus, this disease, has been on the earth for a long, long time. So smallpox was a success story. We no longer vaccinate people for smallpox. Supposedly, the only places the virus is still stored is in the US and in Russia. People talk about the potential for bioterrorism with smallpox, but I think we have other issues right now to deal with. Polio. So polio is a virus. Polio most of the time does not cause any issues. It replicates in your gut and it leaves. Sometimes polio can get into the nerve cells and then it can cause paralysis. With the advent of indoor plumbing, we saw a spike in the incidences of poliovirus in the US in the 1940s, 1950s. And it was devastating. Children were in iron lungs, their muscles weren't working, they were in braces, and so there was a huge fight to end polio. And as of, 2016, we're really super close. Okay. 99% of the way eradicated. Okay. And this is showing you 4 countries in the blue here that still have some wild poliovirus that they can monitor. The green, potentially. The gray, it's been certified polio free. Now, as you know, with world travel, that can all change, right? So we are still vaccinating for polio. And the reason this one is so challenging is polio is a naked virus. Remember, which means it does not have an envelope, so it's very stable. And so it can actually hang out in the environment. It can hang out in chlorinated water. It can hang out in the soil. And so there's a chance that people could still be infected with poliovirus. The other issue with poliovirus is basically due to the vaccine. So there are 2 different types of vaccines. There's an oral and there's an injectable. Okay. And the oral vaccine, also called the Sabin vaccine, is what we call a live attenuated. So this is a weak virus. The virus doesn't cause disease, but it does replicate, which means people given the oral poliovirus vaccine will actually produce virus. Polio is transmitted through the fecal-oral route, which means they poop out the virus, and you can imagine virus could be shed into the environment. Okay. So you still have live virus. The reason this is such a good vaccine is it gives you the best immunity. Okay. So having a weak virus replicate in your system really sparks that immune system and makes a very strong, long-lasting immunity. Also, because you are shedding virus, you can get what we call secondary spread, which means even if someone wasn't vaccinated, they can be exposed to this weakened virus and get immunity. Right? The issue and the reason we do not use the live attenuated virus in the United States is virus-associated paralytic poliomyelitis. Virus-associated Paralytic poliomyelitis, I think. What we were finding is that 1 in about 2.4 million cases of people who received the vaccine would actually develop paralysis. So this is a live, weak virus. It can replicate, it can mutate, and sometimes it would cause disease. So we stopped using that in the States and in other countries where polio has been basically eradicated, and switched to the injectable Salk vaccine, which is what we call an inactivated virus. And what that means is that the virus cannot replicate, cannot cause disease. And so it gives you a little bit less immunity. It's not quite as long lasting, it's not quite as robust, but it's 100% safe. So the trade-off, right, is if you can get everybody immunized, this is a fine vaccine. If you're in places in the world where it's hard to reach every single person, using a live attenuated one that can potentially spread to those people you haven't been able to get the vaccine to has an advantage. Okay. They are talking about perhaps having to switch over to the Salk vaccine so that no more live virus is shed into the environment. That may be our only way to eradicate. But we're really close. And what's interesting for me is back in the late 1990s, when I was in graduate school, we were really afraid that they were going to eradicate polio. And my research was on poliovirus. And I thought, oh my gosh, I'm never going to get my PhD. I'm going to have to start all over. And good or bad, they did not get it eradicated in time. So I graduated. Vaccines have gotten a bad name due to one person's false research publications. Andrew Wakefield claimed a link between vaccines and autism. Okay. This was in 1998. Published these papers. People freaked out. They stopped vaccinating their children. And you can see that we started to get this increase in measles and mumps. Okay, so he said the MMR vaccine, which is measles, mumps, rubella, we'll talk about that in a minute, was causing autism in children. Unfortunately, even though his research has been shown to be fraudulent, he falsified information. He only reported the data that went along with his hypothesis. He had financial conflicts. There are allegations of him abusing some developmentally challenged children. Just awful stuff. Kind of like the fake news we have right now. Once that gets out there, people don't want to change their mind. And so that's why I mentioned that you now have to go through this paperwork to prove there is a good reason for you not to get a vaccine, not just because you're scared of it, because vaccines are so important, protecting our children and protecting the population from these diseases, and measles and mumps are viruses that we had under control. The concept of herd immunity kind of helps us with this. And this is where I talked a little bit about the secondary infections, and this is what we're counting on right now with people not getting immunized. Okay. So when no one or very few people are immunized, everyone can get sick, right? When you start bringing in the vaccinations, so the little green or yellow people are immunized and healthy, you start to see lower numbers. But the more you vaccinate, the more you protect the rest of the population. Okay. If a contagious disease does not have a host, it can't replicate, it can't get passed on. So unfortunately right now we have to rely on some herd immunity, even in the United States, to try and keep those people who are choosing not to be vaccinated healthy. And trust me, I hated taking my kids in for shots all the time, but to prevent a disease that they never have to get, it's worth it. So let's talk about the different types of vaccines that you could be receiving. One is called live attenuated, and we just talked about that with one of the polio ones, the oral polio. So this is a virus or a bacterial cell that's weakened but still replicates. Okay. And this, gives us the best, longest lasting immunity. Okay. The next type we have is inactivated. Okay. So you still have the entire virus or you still have the entire bacteria, but it's chemically treated, and you can kind of call it dead. Okay, it cannot replicate, cannot cause disease. This is second best. So this gives you good immunity. But for some diseases, some pathogens, some things we are trying to prevent, you can't use the whole virus. You can't use it attenuated. You can't use it bacterial. It either is too hard to grow up, that type of virus doesn't work, or it's too dangerous. So we use things called fractions, which is really just parts of the pathogen. So remember, our goal here is to make antibodies and memory T cells that will protect us against a challenge with the real thing. So, for instance, if a bacteria like diphtheria or tetanus produces a toxin, we can use part of that toxin as a toxoid and stimulate your immune system so that if the toxin gets into your system, you have antibodies ready to destroy it. Protein subunits, same idea. You take something from the outside of the virus or the outside of the bacteria, and you just use that little piece to stimulate the immune system. Polysaccharides, remember polysaccharides is that outside of the bacterial membrane cell wall. So you would express some of those polysaccharides in the vaccine so that you mount an immune response to that. And conjugates means sometimes you have to link something to your fraction. Okay. So you've got to give it this extra boost. So for Haemophilus and meningococcal and pneumococcal, they use something called a conjugate. So the take home from this is These are also good immunity. Sometimes you need multiple boosters to keep that immune system primed, but these are just pieces of the pathogen versus the whole pathogen. So, what about all the vaccines that we're giving people right now? So the DTaP is diphtheria, and you don't have to know these, I'm just giving it to you for FYI. Tetanus, pertussis. Okay, these are two toxoids. Pertussis is the bacterium that causes whooping cough. Okay, this is an old vaccine, been around forever. MMR is measles, mumps, rubella. These are 3 viruses. These are all live attenuated. Again, darn it, been around a long time. This is the one that Wakefield said was linked to autism. Polio, like I said, is a virus, and we have the oral and the injectable. These guys are bacterial, and these are all fraction vaccines, all against the polysaccharide, or the capsule. Influenza is a virus. Oh, and just in case you didn't know, this is, hopefully I spell this right, Haemophilus, Influenza B, and it is a bacteria, even though it sounds like influenza, the virus. So you know that the influenza virus, we have a new developed vaccine every year. We'll talk about that in a minute. There are vaccines for hepatitis A, hepatitis B. A is an inactivated virus. B is a fraction. It's part of the surface antigen. And the problem with hepatitis is it can cause liver failure and cancer. So we're really trying to prevent against those long-lasting diseases. There is also a hepatitis C virus, but we do not have a vaccine for that. Rotavirus is what causes the stomach flu. This is an attenuated virus vaccine. Varicella is for chickenpox. This is also an attenuated virus. And what's interesting is that you can develop shingles from the varicella vaccine. So I'm not quite sure. They must not be able to make a inactivated virus that gives enough immunity. So don't think that just because you got the chickenpox or you got the chickenpox vaccine that you're protected. HPV is human papilloma virus. Okay, and the goal for here is cancer prevention. So the HPV vaccine is being given to boys and girls now at fairly young age. They try to do it before they're sexually active because there has been a little bit of concern that if you give the vaccine after someone's been sexually active, it could actually cause or increase your risk of cancer. So trying to hit people early, but this is one of the much newer vaccines, and again, it's to prevent cancer. Most of the time, if you get a papillomavirus infection, you clear it or you get warts. There's also vaccines if you're traveling, or if you're in the military, or if you work with animals, say, you may get the rabies vaccine, or if you're in the military, you may get a vaccine against anthrax, or if you're traveling, you may get a vaccine against yellow fever. Things that we don't normally encounter in the States, we do have special vaccines for people traveling. So influenza. Why a shot every year? Well, influenza can mutate rather quickly. And when it mutates, it changes what it looks like on the outside. And you know from the immunology lecture that it's what's on the outside that things like your antibodies recognize. They recognize the antigens. And so if the virus changes enough so that it looks different, then you don't have a secondary immune response ready to go when this virus comes in contact. So researchers look at how influenza is changing each year. They try to develop a new vaccine. Some years it's really good and prevents people from getting sick. Some years it's not so good. We're also finding that the number of people getting the flu shot has really decreased. So we had that kind of scare several years ago with H1N1, and everybody was getting vaccinated, and then nothing really happened with it. And so now the vaccination rates are a lot lower for influenza. Just an FYI, the injection is an inactivated virus. So no, you cannot get sick from getting the flu vaccine, even though people like to say they do. The nasal spray, on the other hand, is an attenuated virus. And it's attenuated or weakened so that it can only replicate in the cooler temperature of your nasal cavities. So if you suck it in down into your warm body, the virus dies. It doesn't work, it's not alive, but doesn't replicate anymore. So it's a temperature sensitive mutant. And again, the vaccines that you get each year, if you choose to get them, are combinations of what they think the flu is going to look like as it moves across the world. Tuberculosis. Okay, so tuberculosis is a bacterium. They have had a vaccine since 1921. Oldest vaccine still in use. You'll see it called the BCG. It tends to protect against childhood tuberculosis, but not pulmonary, so tuberculosis in the lungs of adults, and not tuberculosis in all parts of the world. So there's enough difference in this bacteria, enough different strains, that we have not been able to make a good vaccine. And you'll notice that in this country, the tuberculosis vaccine is not even on the list. Immunity lasts only 10 to 15 years, and it has very, very variable protection. Oops. So it's just not used. this is a vaccine that people are still working on. Tuberculosis is a huge issue in other parts of the world, but we still haven't been able to figure out how to prevent this bacterial infection. Other vaccines people are working on, of course, a vaccine for HIV. Right? This virus mutates so rapidly that we have yet to be able to make a protective vaccine. Now, every few years, someone comes out and says they have made one, and then they usually do further testing, and it shows that it's not protective. So it's mainly due, again, like influenza, the issue is the high mutation rate of the virus. Another vaccine that's in development is against malaria. And remember, malaria is caused by a protozoa. Last I looked, there was 11 different vaccines in trial. But again, they have not been able to make a protective one. So we will talk, we have a Neisseria vaccine, a dengue virus vaccine paper, and so we will talk more about the issues with developing vaccines. So that's your lecture on vaccines, and thank you.